Hi everyone, this is going to be a lesson on logarithmic functions. Some of you may have seen logarithmic functions before in an algebra class, but it turns out that they are pretty important for calculus, and since this is pre-calculus, we want to hit all of the important topics. I'll tell you that the short version of it is that logarithmic functions are the inverses of exponential functions. So we just spent 2 sections talking about exponentials, and logarithmic functions are kind of the other side of the coin. They're closely related. So hopefully everybody was comfortable with the exponential functions. All right, so let's go ahead and get started. So I just said something a moment ago about how logarithmic functions are going to be the inverses of exponential functions. And what I'd like to do is spend a little bit of time, maybe about 1 page, doing a quick review of what it means to be an inverse. All right, and in order to do that, we need to start with a definition. And this is not a definition for logarithmic function. A couple of definitions we need before we can get there. All right, definition. A function f is one-to-one if no two inputs have the same output. We can think of a function as a rule that has inputs and outputs. You put something in, usually the thing you put into a function is called x, and you get something out, and usually the thing you get out is called f of x. Well, we're talking about 2 inputs. So if we write this in symbols, this would say f of x1 is not equal to f of x2 whenever x1 is not equal to x2. So both of those sentences are actually saying the same thing if you look at it closely enough. First sentence says no 2 inputs have the same output. The second sentence says the outputs are different whenever the inputs are different. So, for example, is the function f of x equals x squared one-to-one? And if we were doing this in person, usually I would ask the class, yes or no, what do you think? Is this one-to-one? I would ask you to think about it. And usually someone would speak up and say, no, it's not one-to-one. And the reason is because we can find 2 different inputs that have the same output. For example, if I did f of -1, I get 1. If I do f of +1, I get 1. Because -1 squared is 1, +1 squared is 1. So these are 2 different inputs. You could think of them as the x1 and x2. They're 2 different inputs that got us the same output. You can also think of other examples. Do f of -2 and f of +2. So there are lots of reasons why this function is not one-to-one. So this idea is that one-to-one is a property that some functions might have and some functions might not. In this case, we were able to sort of tell by observation, by finding a counterexample, we were able to tell whether it was one-to-one or not. There's another way that you can tell, and it is called the horizontal line test. So first of all, in a sentence, it says, a function is one-to-one if and only if no horizontal line intersects its graph more than once. So, let's see. Let me draw a picture here. I'm going to draw a picture of f of x equals x squared. We know what that looks like. That's the classic parabola, passes through the origin. We're probably going to draw it a bunch of times this semester. So pass through the origin, goes something like this. Label some scale here, 1, 2, 1, 2. All right, so what does the horizontal line test look like? Well, we imagine, you can draw it or you can imagine it, imaginary lines. Can you make a horizontal line that intersects this graph more than once? And I would say, yes, we can. We could do like a horizontal line here, boom, intersects the graph more than once. Therefore, this function is not one-to-one. As soon as it intersects more than once, you might say that this function fails the horizontal line test. It fails to be one-to-one. And we did say above, no, it is not one-to-one. If we drew a horizontal line down here, that doesn't intersect the graph at all. So that's really inconclusive. That doesn't really tell us anything. The idea is there a horizontal line somewhere that intersects it more than once? And yes, there are places where a horizontal line is going to intersect it more than once. It means it's not one-to-one. By the way, look at this latest line that I just drew. This horizontal line crosses through the graph more than once. Where did it cross through? This one crossed through the point 1, 1, and -1, 1. What I'm trying to show you is that up here, above, didn't we say f of -1 was 1 and f of 1 was 1? So that's not just a coincidence. This is basically saying that the graph passes through that point. This is saying the graph passes through 1, 1. So the horizontal line test works because it's basically checking for this. It's basically checking for the definition of one-to-one. And then I guess just because, so this is not one-to-one. Since I gave you an example of something that's not one-to-one, let me give you a quick example of something that is one-to-one. Let's see. What do we want to do? It's going to keep it simple. I don't know. X plus 1. The function x plus 1. Simple function. It's a linear function. Has a slope of 1. Y-intercept of 1. We can draw that. There's the y-intercept of 1. Slope is 1, so for every 1 unit we go over, we go 1 unit up. All right, I just wanted to give you one example of something that is one-to-one. And if you notice, any horizontal line that we try to draw, whether I draw it up high here or if I draw it lower, it is going to pass through the graph only once. We're never going to find a horizontal line that passes through this graph more than once. So this is one-to-one. And it actually seems like you could come up with a lot of linear functions that are one-to-one. There are other functions as well, not just straight lines, not just linear functions. All right, so this section is supposed to be called logarithmic functions. And I said that before we get to logarithmic functions, I wanted to spend some time talking about inverse functions. So what's going on here? We're talking about this property called one-to-one. And the big question you should be asking yourself is, why do we care if a function is one-to-one? Why do we care if a function is one-to-one? The reason is because of this definition. Let f be a one-to-one function. So we're assuming that we have a one-to-one function now for this definition. Actually, furthermore, with domain A and range B. All right, we're specifying the set of all x inputs and set of all y outputs. Then there is an inverse function. And it's written as f with a little -1 up there. It looks like f raised to the -1. It's not really being raised to the -1 as like an exponent, although it is written that way. There is an inverse function with domain B and range A, so that, did you notice that the domain and range kind of swapped places? Instead of A and B, it went B and A. So that f inverse of y equals x whenever f of x equals y. This is why we care if a function is one-to-one or not, because one-to-one functions have inverse functions, and inverse functions are going to turn out to be important. What an inverse function is it's a function that, well, from this definition, what can we tell? Let's say f of x equals y. So f of some value of x equals y. The inverse is taking in y and giving us x. So it's kind of sending this was the output of f. It's the input for f inverse. So basically, it's doing what f did, but in reverse. All right, key idea. We pronounce it f inverse, and I'm going to say f inverse undoes whatever f does, and vice versa. Okay, so an inverse function basically does what the original function did, but in the opposite direction, kind of in reverse. So you have a function that does something, then you get an inverse that does the opposite. In symbols, I can kind of demonstrate this. So two facts. If you actually have an inverse function and you did f inverse of f of x, so function inside a function. So what would happen here? Well, you're supposed to work with order of operations. So you do the part in parentheses first. So you look at f of x first, and then you do f inverse of it. You have x, you apply f, then you apply f inverse. Well, when you apply f, it does something to x. When you apply f inverse, it does the opposite. It undoes what f did, and it just gets you back to where you started. It just gets you x. Similarly, if we did f of f inverse of x, you also just get x. This is saying that the function and its inverse, they sort of cancel each other out. That's what it means to be an inverse function. Off to the side, I'm going to say side note. we could use these two facts to verify that we have found an inverse function. So, like, if you have something that you think is an inverse of something else, you could run it through these two facts and make sure that they do both wind up equaling x. Let's move this up a little bit. Let's do a quick little example of a function and an inverse. By the way, an inverse function doesn't have to be called f with the little -1 next to it. It could go by a different name, and it could still technically fit the definition of being an inverse function. So for this example, I'm going to have f of x and g of x. And I'm going to tell you that these are inverses of each other. Can you tell that x cubed and the cube root of x are doing the opposite of each other? They kind of do the reverse of each other. They would cancel each other out. For example, what's this business up here about like f inverse of y equals x whenever f of x equals y? That was in the definition. It seemed important enough to be in the definition. Let's put in some actual numbers and see this happen. So if I did f of 2, f of 2 is 2 to the third power. So 2 times 2 times 2 is 8. Okay. What if I do g of 8? G of 8 would be the cube root of 8. The cube root of 8 happens to be 2. So that's what's happening here. That's this sort of swapping of x's and y's that take place. If the function f of 2 gives us 8, then we know that the inverse g of 8 is going to give us 2. Also, I'm going to do this side note that I said. I'm going to verify these two facts. I'm going to show you that it works. So like if I do g of f of x, we have a name for this sort of thing. Remember, this is called composition of functions. When you put a function inside another one, it's function composition. In this case, it would be the cube root of x cubed. What's the cube root of x cubed? I think in order to simplify this, maybe I would think of the cube root as raising to the 1/3. Taking the cube root of something is the same as raising it to the 1/3. That was one of those properties of exponents. And now we have x to the third to the 1/3, and there was a property of exponents that said you can multiply the exponents. 3 times 1/3 is 1. So this does simplify to x. I'm going to put a little check mark next to it, because that is what we were expecting to see. What if I do it the other way around? F of g of x in this example, it would be the cube root of x, and then that is getting cubed. Again, I think that I'm going to deal with this by thinking of the cube root of x as x to the 1/3. And again, we get two exponents. We have x, you want to raise it to the 1/3, then you want to raise it to the 3. And there was a property of exponents that says you can just multiply these two exponents, so you get x to the 1. So yes, this does check out. It does satisfy both of these facts, and that's one way to verify that these are in fact inverses of each other. Something I kind of skipped over is explaining that these functions happen to be one-to-one, but that's okay. I mean, you could graph x cubed, or maybe you remember what the graph of x cubed looks like, and it does pass the horizontal line test. So we just spent about 20 minutes, a little bit more than one page, talking about inverse functions. We had to spend the first half of it talking about what it means to be one-to-one, and then we spent some time talking about inverse functions. What we really want to talk about is logarithmic functions, and now I feel that we are ready to talk about that. So I want to point out, note, if a is greater than 1, then f of x equals a to the x is 1-to-1. All right, exponential function where the base is greater than 1. We drew this in a previous video when we first introduced exponential functions, and we said that an exponential function in this case looks something like this. What I'm saying now is that it's 1-to-1 because it passes the horizontal line test. There's no horizontal line that's going to pass through this curve more than once. So it is 1-to-1. That means it does have an inverse function. Also, what about the other case? The other case was if a is less than 1. Is that kind of exponential function also 1-to-1? Yes. Because in that case, the picture looks something like a horizontal flip. I mean, you know, the exact steepness and the exact shape of this depends on exactly what a is. But this is the general idea, is that exponential function graphs fell into these two cases. And now I'm saying that I can tell from the horizontal line test, no horizontal line is going to cross through this more than once. Some horizontal lines are going to not cross through it at all, and some horizontal lines are going to cross through at one point. So exponential functions have an inverse. F of x equals a to the x has an inverse, which is going to be a function that does the opposite. You know how exponential functions, we said they grow very rapidly. So like if I had an exponential function and I put in an x value like 10, it's going to probably make it grow very, very large. There's some kind of inverse that does the opposite, that takes large numbers and makes them small. We have a way of writing this. We write as, well, we could write it as f inverse of x. We could write it that way, but it turns out that this comes up so often in mathematics that it just has its own name and it has its own way of writing it. And that is going to be log with a little a down here of x. And we call it the logarithmic function. With base a. So every exponential function had a base. Every logarithmic function has a base also. So from this point onward, I probably won't write these as f inverse. I will probably just use this log notation. But we understand that log base a of x is the inverse function of f of x equals a to the x. By the way, another way that this is sometimes written is you can also write it without the parentheses. All right, sometimes we'll do the parentheses, sometimes we won't. It's optional. A key idea about logarithmic functions, or we might just refer to them as logarithms. A key idea about logarithms is that log base a of x equals y whenever a to the y equals x. All right, those are y's. I know sometimes my y's look like 4's. Log base a of x equals y whenever a to the y equals x. It can be tricky to keep track of all the a's and x's and y's, but I think some examples will help. So we'll do some examples in just a moment. But, you know, where is this coming from? Like, what is this all about? That is coming from what we said earlier, which I'm just going to show you real quick. This line right here. All right, I'm going to underline it. This line right here is this line right here when we're talking about logarithmic functions. There's this kind of swapping of x's and y's that takes place when you go from a function to its inverse. That's what makes sure that your inverse function is doing sort of the opposite, or going in the opposite direction. All right, so I said I was going to show some little examples of this. So let's just do some quick logarithm examples. So for example, I know that 2 to the 3 is 8. That's just, that kind of looks like a to the something equals something, right? Number to the something equals something. And the idea is that we could write a logarithm with base 2. 2 would be the base in this expression. 2 is being raised to a power. So we could write a logarithm with base 2 of 8 equals 3. So if somebody asked you, what is a log base 2 of 8? It's 3 for this reason. It's 3 because that is the number that you would have to raise 2 to in order to get 8. 2 needs to be raised to 3 to get 8. So log base 2 of 8 is 3. 9 to the 1/2 is 3. So log base 9 of 3 is 1/2. Anytime you write a little exponential expression like this, there is a corresponding logarithmic equation. 4 to the -1 is 1 over 4. So, what do you think I'm going to write here? Log base 4 of 1/4 equals -1. So logarithms, very often logarithms can be evaluated without a calculator by thinking about what they represent in terms of like exponents. Here, I'll give you an example. I'll ask you to try this. Example, if y equals log base 4 of 16, what is y? So think about this for a minute. See if you can figure that out without a calculator. All right, so the way that I'm going to think of this solution I'm looking at that equation, y equals log base 4 of 16, and I'm saying that, you know, this means 4 to the y equals 16. Like if we do this sort of converting back and forth between log form and exponential form, the base is 4 because the 4 is appearing next to the log. So it would be 4 raised to something. It would be 4 raised to this. So 4 raised to y equals 16. And we want to know what is y. So I ask myself, do I know what number would have to go here? 4 to the something is 16? Yeah, that means that y has to equal 2. 4 to the 2 is 16. So log base 4 of 16 is equal to 2. A lot of problems are going to be set up where the answer is, either like a whole number, or maybe an integer, but maybe it could be like a fraction like 1/2 or 1/4 or things like that. But there'll be a lot of things that we can do by hand. Now, this section is about logarithmic functions, and we're getting used to kind of dealing with logarithmic expressions. But then you think, what are some of the things that we like to do when we talk about a new type of function in a math class? Well, we like to talk about the domain and range. I'll give you a hint of what's coming next is talking about a new type of function. We like to talk about domain, range, and then probably the graphs. We'll talk about the graphs of logarithmic functions. They're not the same as the graphs of exponentials. All right, so real quick, let's say we have an exponential function, a to the x, and let's also consider its inverse, which is log base a of x. We know the domain of f is all real numbers. And we know the range of f is... Do you remember what the range... I'm speaking to a video here, but I'm asking you to think about it. Do you remember what the range of an exponential function is? Hopefully you remember it's 0 to infinity with curved parentheses. That was in a previous video. From this, we can figure out the domain and range of the inverse version of it. I'll tell you what I'm going to use. Earlier, we had a definition of inverse function. Remember it said something about domain A and range B, or domain B and range A? If you look back at that definition, when you go from a function to an inverse, the domain and range swap places. So because of that, the range of the inverse is going to be all real numbers, and the domain of the inverse is going to be 0 to infinity. We go from an exponential to a logarithm, the domain and range swap places. So what are some things that we could take away from this? I would say that in math, when we talk about domain and range, usually domain is kind of the more important one. And the reason I say that is because if you think of a function as like a rule that has inputs and outputs, domain is telling us what we are allowed to input. It's a set of all inputs. This right here is telling us the only things that we are allowed to input into a logarithm are things that are greater than 0. So we can't take log of a negative number, or 0 for that matter. It would be undefined. It would not be in the domain. And I usually think this is kind of reminiscent of like when we do square roots, we typically don't want to do a square root of a negative number. Usually, because we're usually working just with real numbers. So usually we say square roots. I don't want to take a square root of a negative number. With logarithms, I don't want to do a logarithm of a negative number. Now, you could still have a problem in this section that involves negative numbers in some way. Look at this up here. There was a -1 here. But that's not the thing that's going into the logarithm. We do log base 4 of 1/4. 1/4 is a positive number. 3 up here, positive number. 8 up here was a positive number. 16 over here was a positive number. So you could get an output that's negative. You just can't put an input in that's negative. Now, I said we wanted to talk about the graphs of logarithmic functions, and the graph needs to somehow depict what we just said about the domain, like negative numbers don't work. Now, for exponential functions, there were two cases when we drew them. So for logarithmic functions, there's also going to be two cases. Graphs of log functions. Now, I was thinking about drawing the original exponential cases, and we'd have like two pictures of those and then two pictures of the log graphs. But how about we just draw the log graphs? I think that would be okay. So, again, two cases. Let's set up two xy planes. First, I'm going to try to draw y equals log base a of x, where a is greater than 1. And the other one is going to be y equals log base a of x, where a is between 0 and 1. Okay? Let's see. You know how for the exponential graphs, they both passed through the point 0, 1. That was a y-intercept for both of the exponential cases. 0, 1. I'm not shading that dot in just yet. Just trying to remind you of that. When we switch to the log version, because of this swapping of x's and y's that take place, instead of passing through 0, 1, we're going to pass through 1, 0. All right? 1, 0. And that's going to happen in both cases. Remember how the exponential graphs have a horizontal asymptote at the x-axis? Well, the log versions, because we're doing an inverse, we are swapping x's and y's. Instead of having that horizontal asymptote, it's going to have a vertical asymptote on the y-axis. Both of them. Both cases. Kind of hard to draw, an asymptote that's right on the y-axis, but I think we did pretty good. And the overall shape, in a way, is not that different, but we need to approach the asymptote and not cross it. We need to pass through that x-intercept. So what's going to happen is, in the first case, we get a graph that looks something like this. And in the second graph, we get something that looks like this. In fact, if we want to be more technical about this, if you compare these with the original two graphs of exponential cases, you actually get these graphs by taking the original one and reflecting it across the line y equals x. The diagonal line. So like where I just put my pen would be the diagonal line y equals x. the exponential function would kind of be over here. And we're kind of flipping across this diagonal mirror to get this reflection over here. But yeah, these are the two cases. And notice that in both of these, it does show the domain that we're expecting, where the graphs are only defined for positive x values. There's nothing over here to the left. It's undefined over here. Same thing in the second case. It also shows the range that we were expecting. The range is all real numbers, which means you can get any possible y value. So you can go all the way down, down, down here to like, negative y values. You can have a y value of 0. And it also continues growing upward forever. But whereas exponential functions are known for growing very fast, logarithmic functions are actually known for growing very slowly. As this continues to go to the right and up, it continues to go up, but it goes up slower and slower and slower, but it continues to go upward forever. All right, so far in this section, we've talked a little bit about what inverse functions are. We've talked about what logarithmic functions are. We've seen some little examples up above of some logs. And we talked about domain, range, and graphs. What I'd like to talk about next are two important bases. And they are E and 10. You know, the base is the thing that we've been calling A. You know that when we talked about exponential functions, we had an entire lesson on the natural exponential function. That was the function e to the x. So if that's such an important exponential function, what about the logarithm version of that, like the inverse version of that? So let's talk about that. Base e. Let's talk about that one first. So f of x equals e to the x, which had its own section, has an inverse, as all exponential functions do, log base e of x. However, we have a special name for this, and we actually have a different way of writing it. So we call this the natural logarithm. And we write it as ln x instead of log base e of x. So the natural exponential function has an inverse called the natural logarithm. And it's written as ln x. It means log base e of x, but it's written as ln x. So from now on, I will only call it ln x. I wrote over here, log base e of x, log base e of x. But when you work with these long enough and you just get used to calling it ln x, it kind of looks weird to me to even write it as this other way. Log base e of x looks weird to me. Ln x is what it's best known as, so that's what I'm going to call it from now on. I want to tell you that key idea that I wrote about 10 minutes ago. I want to rewrite that key idea in terms of this logarithm, and that's going to say ln of x equals y whenever e to the y equals x. And all of the same rules apply All the same rules apply, like the domain and range that we're expecting. Like not taking a logarithm of a negative number, stuff like that. Let's talk about let's quickly talk about base 10. So f of x equals 10 to the x has inverse. Well, it should be log base 10 of x. We call this the common logarithm. And we write, this one might seem a little weird at first, the way we write it. We write it as log x instead of log base 10 of x. So what I'm saying is, if the base is 10, we just write it as log x. We don't even write the little 10. So if you ever see a log of something, if you see like log 5 or log 20, and there's no little number next to it, it's just log something, there's no little number, there's no base indicated, it is implied that the base is 10. Now, the natural logarithm, I'll tell you, we use the word natural because it shows up a lot in sort of the natural sciences, physics, chemistry, things like that. Astronomy. Shows up in lots of places. The common logarithm tends to show up more in things like units of measurement that we've invented. Just because we have a base 10 counting system, there are some real-life applications where base 10 is useful. So we might need both of these for pre-calculus and calculus. And you know what? I'll show you an example. I'll show you a word problem before we finish today. But I think we have something else that we need to talk about first. All right, so the something else that we need to talk about first is I have some questions for you to think about. I want to ask you, what are the following? You know how earlier I asked you a question like 4 to the y equals 16, or I guess I asked you like what's log base 4 of 16? We figured out that it was equal to 2. I have 4 questions for you that are kind of like that. Okay. Log base 8 of 1. Log base 8 of 8. Log base 8 of 8 cubed. And 3 raised to the log base 3, 7. So I'd like you to take a couple of minutes, try to figure these out without a calculator, just using what we said earlier about what log means. All of these equal just some normal integer. There's no weird decimals or anything. So it would be good to pause the video, think about this for a couple of minutes, and then I'll talk about it. So to talk about these, I might actually want a whole new sheet of paper because I want to discuss each one of these. I'd not just give you the answer, but let's figure out why the answers are what they are. Okay, so those were questions. These are answers. Part A. You know, if we were doing this in person, I would ask you for what the answers are, but that's okay. Log base 8 of 1. Hopefully you found that this equals 0. And I'm going to tell you my reasoning here. How do I know that this is 0? It is because if I think of what log base 8 of 1 represents, in terms of exponents, the base would be 8, so it would be 8 raised to a power. And it's really like saying 8 to what power equals 1. 8 to what power equals 1, and the only answer that can go there is 0. That's how I think about these problems sometimes. If I have a logarithm, sometimes I rearrange it into something involving an exponent. It's like we were trying to find the exponent, which has to be 0 in this case. Now, I said I wanted to discuss each one of these. What I wanted you to notice here is that the 8 doesn't really seem important, does it? Like, if I gave you this same question, but instead of an 8, if it was like a 7, the answer would still be 0, because 7 to the 0 is 1. If instead of an 8, if that was like 2 million, the answer would still be 0, because 2 million to the 0 is 1. So we get a general fact from this that log base A of 1 always equals 0 for any base A. I'm going to put a box around that. Anytime you see log something of 1, it's going to equal 0. All right, I think I can move the page up. I think we all saw the problems long enough. I'm going to write each of these as I answer them anyway. So part B was asking about log base 8 of 8. And again, I think of this in terms of exponents. It's like 8 to what power is 8? So this is going to equal 1 because 8 to the 1 is 8. And what I was hoping you would notice here is that there's nothing particularly special about the number 8. What matters is that they were both 8s. They were both the same thing. And we can state this as a more general fact. We can say log base A of A is always going to equal 1 for any base A. So log base 5 of 5, log base 10 of 10, they're all going to equal 1. These are useful facts because, you know, later in this section and in the next section, in the types of problems that you're going to see, we can use these facts as like little shortcuts to help simplify things. Like if we have a word problem or we have some other type of problem in the next section, knowing these little things simplify to 0 and these things simplify to 1 is really nice. In math, it's always nice anytime something simplifies to 0, right? Maybe at some point in this course, maybe we'll have something that we can just cross out because we know that it equals 0. That's what we want. That's why we want these general facts. The next one was log base 8 of 8 to the 3rd. And this is going to be 3 because 8 to the 3 is what equals 8 to the 3. That one seems a little weird when I write it that way, but you know, you take the base, you say, what do I have to raise that base to in order to get 8 cubed? Well, it would have to be 3. And we can state this as a general fact as well. We could say log base, well, there's two different numbers involved now. It's not just 8 and 8. It was also a 3 there. I'm going to write this as a log base a of a to the x equals x for any base a and any number x. So the way that I figured out that this was equal to 3 was based on, thinking of it in terms of exponents. There's also another way that you could have seen this. Another way you could have seen that this is 3 is you could have said, I have a log base 8, and I have 8 to a power. Log base 8 and 8 to a power are inverses of each other, and therefore they should cancel each other out. And they do cancel each other out, and they just leave us with 3. So that's another way to see that this could be 3. For the last one looks different from the others, I guess. 3 to the log base 3 of 7. What I was hoping you would find here is that this equals 7. Again, there's two different ways to see it. I think for this one, I want to just think of this as I'm just thinking of 3 to a power and log base 3 are inverses of each other. So maybe I'll just say that 3 to the x and log base 3 are inverses of each other. They should cancel each other out and leave us with just the 7. And we can say this one as a general fact as well if we write it carefully. And this is going to be a to the log base a of x just equals x. And this is true for any base a and any number x. You know what? I think this time I have to say any positive number x. Technically, if we're doing a log of it, x should be positive in order for this to work. Okay. So there, we could fit all of this on the screen at once. These are 4 useful facts. They're useful for simplifying things, all 4 of them, because, sometimes we might be able to use them to simplify something to 0 or 1, but it's also useful sometimes to simplify something to x. Also, if you had an expression given to you like 3 to the log base 3 of 7, that looks really complicated. But then you say, wait a second, that's just a fancy way of saying 7. And that seems a whole lot simpler when you just call it 7. I'll also point out to you that log base 3 of 7, like that part of it alone, is actually really hard to figure out by hand. Like, what is log base 3 of 7? That would be 3 to what power gets me 7? Well, there is a number that does that, but it's going to be some kind of decimal that's hard to figure out by hand. This fact, or this kind of shortcut, means we don't even need to know what it is. Okay, we can just say that these cancel, and that gives us 7. Here, I want to talk more about this because, why not? Side note, what is log base 3 of 7? What is it equal to? This is what I was kind of talking about out loud, but, I'm saying this is some kind of decimal that would be really hard for us to figure out. I'm going to say we know that, let's say 3 to the 0 is 1, 3 to the 1 is 3, 3 to the 2 is 9, and let's go one further, 3 to the 3 is 27. So those are some powers of 3. This is like saying 3 to what power equals 7? That's our question mark. I'm drawing a little arrow here between the 3 and the 9. 7 is between 3 and 9. Okay? So, the answer is between 1 and 2. Do you see that? 3 to what power is 7? It's not 3 to the 1. That gets us something too small. It's not 3 to the 2. That gets us something too big. But somewhere in between 1 and 2, there is a number that goes here and gets us 3 to that number is exactly 7. So I guess we could say then that log base 3 of 7 is somewhere between 1 and 2. So I could say it's 1 point something. And it's difficult to figure out what that is by hand. Maybe we could try to narrow it down further. Maybe we could try to figure out what is 3 to the 1.5. Maybe that's something we could try to figure out by hand, and then narrow it down further. I'm going to show you with a calculator for this one. Show you the calculator. What is log base 3 of 7? So, you know, I don't talk about calculators much in this course, although it seems like we've been doing it a lot lately. My calculator has a button that says ln. I don't know if you can read this, but it says ln and it says log. So you know how I said that there were two important bases and they were e and 10? They're so important that my calculator has ln and log. And I think I actually have to hit the button multiple times before it will let me do a log in any other base. Like I hit the button. This is just for my calculator. Every calculator is different. But anyway, I can do log base 3 of 7. And, oh, look at that. It's 1 point something. So calculator says 1.77 something. All right, that's all I wanted to show you, is that there are going to be some logarithms that are difficult to do by hand, but we could use our intuition or our understanding of how exponents work to kind of get us a rough idea. I knew it was between 1 and 2. In fact, if we had talked about it a little bit more before I reached for the calculator, I probably would have guessed that it was closer to 2 than it is to 1. Because 7 is closer to 9 than it is to 3. So I probably would have said 1 point something, probably on the larger side. All right, so that was just a little side note, and we're going to continue to try to use our understanding of logs in these kinds of situations. I also want to say that the 4 facts above, all of those facts that we wrote above, we said for any base A. So they also work with base E and base 10. But remember, if we're working in base E or base 10, then we write it differently. We might write ln. So in base E, those 4 facts look like ln of 1 is 0, ln of E is 1, ln of e to the x is x, and e to the ln x is x. That's the same 4 facts that we wrote above. We don't need to derive these again or anything like that. It's the 4 facts that we put boxes around above, but this is what they look like for a logarithm of base e, because we write it as ln. This is useful because you might get a problem at some point that has like an ln1 in it. And if you see an ln1, you're going to say that's just 0. You might get a problem with ln e and say ln of e, that's just 1. Ln of e to the x is x, you know. For example, ln of e to the 5th. If I asked you, what is this? It's 5. You don't even have to figure out, like, e to the 5th would be some kind of decimal that's hard for us to figure out, and then we'd be trying to do ln of it. You don't have to. You just say the ln and the e cancel each other out, leave us with 5. You know, over here, for example, if you had a problem that was like e to the ln2, and I said, what does that equal? You could say that simplifies to 2 because the e and the ln cancel each other out. I'm just going to say, you know, and similarly, you can figure it out similarly for base 10. Base 10 would be that the 4 facts above could be written with just log without the little 10 next to it. All right, maybe we've got one more thing I want to do in this section. Seems like we're covering a lot of ground. We're establishing, you know, what logarithmic functions are, getting comfortable working with them. I want to show you a word problem. And in particular, I want to show you a word problem that uses a log of base 10 because we haven't really done much with it. I think I said that the common logarithm is used for some applications. So let's see one of them. So this problem says the loudness in decibels. Decibels is abbreviated dB. The loudness in decibels of a sound with intensity I in watts per meter squared is 10 log I over I10. I'm sorry, I said I10, but I'm writing, it's I sub 0. The loudness in decibels of a sound with intensity I in watts per meter squared is 10 log of I over I0. Where I sub 0 equals the intensity of a barely audible sound. It's kind of like a baseline that the decibel system is based on. I haven't actually asked any questions yet. I'll just mention to you that because this is a math class, I'm not personally, I'm not super concerned about units. I think units are more important if you're in like a science class. So I'm telling you that intensity is measured in watts per meter squared, but I'm just telling you that, but I'm not super picky about units in answers. Okay, part A, there's 2 questions here. Part A, find the loudness of a sound where I is 100 times I sub 0. That's part A. And part B, we're going to do this together. Part B is what intensity I results in 40 decibels. So I'll give you a chance to see all this and write this, but I'm going to talk us through the answer. All right, so part A. Let's get started. Part A, solution. We want to find the loudness of a sound. Okay, the problem told us the loudness of a sound with intensity I is this. Okay, find the loudness where I is 100 times. Look at this. We are given that loudness is 10 log I over I sub 0. Okay, that's given in the first sentence. And we're also given in this part of the problem, it says I is 100 times I sub 0. All I did was take these words and turn it into this. It says I is 100 times I sub 0. So I wrote I equals 100 I 0. Okay, no big deal. All right, so the loudness that we want is going to be 10 log. Let's substitute this in. I is 100 I sub 0 for this part of the problem. The nice thing about doing this is we have an I sub 0 over I sub 0. Those cancel out. Number divided by itself is 1. So this equals 10 log 100. Side note, what does log 100 equal to? It's like a little problem within the problem. Do we know what that is? Well, I would say that this is the same as saying, remember that when it says log with no base written, if there's no base indicated, there's no little subscript, no little number, it's implied that the base is 10. So this is the same as saying 10 to what power equals 100. And we know what that is. That's 2. So this whole thing here is 2. So we have 10 times 2. Answer is 20. And I'll write decibels because that is the final answer. The loudness is 20 decibels. All right. By the way, if you've ever heard of sound being measured in decibels, if you're wondering where the deci comes from, deci is because we're working in base 10. All right. Let's see what we can do for part B. What intensity I results in 40 decibels? So the loudness is given. It's 40 decibels. So let's set this up as 40 equals 10 log I over I sub 0. I guess in this problem, in this part, we want to find capital I. We want to solve for capital I. We might not be able to get an actual number for this because the way the problem was phrased, we weren't really given a specific number for I sub 0. I think we're going to find I in terms of I sub 0. We'll work with this and we'll see what happens. We'll do the best we can. I think the first thing I would do is I see a 40 and a 10, and I would say let's divide both sides by 10. Divide both sides by 10. It's going to make things a little simpler. All right? Looks a little simpler already. Here's what I'm going to do. I'm going to kind of section this off from part A so we don't get mixed up. Okay. This is the same as, you know how earlier I was saying we can kind of convert back and forth between like something in log form and something in exponential form, and we kind of did that up above in this side note. I'm going to do it again. I'm going to say the base is 10. This is like saying 10 to the 4 equals, what were we taking the log of? I guess it's this thing, I over I sub 0. Does that help us? Well, yeah, it gets rid of the log. And let's work with this way. 10 to the 4 is 10,000. And now we can solve for I. This question was asking, what is the intensity I? The answer is I equals 10,000 I sub 0. So we got an answer for what I is. I is 10,000 times I sub 0. All right, so that's a word problem involving logarithmic functions. In particular, it was involving base 10. What else can I say about this? I guess it's kind of interesting that, you know, the decibel scale is set up so that if, you know, something is 20 decibels, that's 100 times louder than a barely audible sound. If something is 40 decibels, it's 10,000 times louder than a barely audible sound. I guess I shouldn't say it's 10,000 times louder. I guess I should say it's 10,000 times more intense than a barely audible sound. Because this problem was making a distinction between intensity and loudness. All right, and you could also get word problems that use logarithms with other bases. Maybe base e is one of the other ones that comes up a lot. Maybe base 2. Or you could get some problems that don't involve word problems at all. You could just get questions like, what is log of 100? You know, what is log base 4 of 16? You know, things like that. Okay, so that was our lesson on logarithmic functions. And we do have 2 sections about logarithms. So the next video lesson that you see is going to be more of this. I would suggest that it's good to make sure you understand the stuff from this video before you move on to the next one. You know, do some practice problems, work on some homework, ask questions if you have questions. You know, make sure you understand like the overall idea behind logarithms before you move into the next video. So the next video, we're going to do some more properties of logarithms. Kind of like the 4 facts that we had today, we're going to have 3 more sort of facts or properties. All right, so I guess that's it. So thanks for watching, and I'll see you next time.